make sure that there was one concept that I kind of stumbled on yesterday, and I apologize. I'm human. I make mistakes. But I want to make sure I kind of backfill that, make sure we're good with it. Okay, so on page 75, and we're just going to go through this as a class, being if you're here, you're going to get the points for it. If you're not here, well, then they better watch the video so they can get the points and figure it out, right? Yeah. All right. Problem number 1 says, we seek to find the average number of left-handed students in any given class. Okay. People who use their left hand versus their right. We sample 40 different classrooms. Explain how sampling variability would take place. Okay. So we're looking at sampling variability takes place. Variability. I think I spelled that right. I guess so. All right. So we're looking for people with left hands, or using left hands, left-handed people. Okay. We're going to go to 40 different classrooms. Okay. So I think we're just collecting data here. We're not trying to verify that a certain percent of the population with standard deviation. I think we're just collecting data. Agree? So let me just ask this. If you feel comfortable telling me, who is left-handed in here right now? Got one? Okay. Got none. So we got none. Now, it is possible when everyone else gets here, somebody who would show up might be left-handed. So do you think there's any rhyme or reason if we were to have 40 classrooms, which I imagine we could identify 40 classrooms in this building alone that probably have a class in it right now? Do you think me going classroom to classroom that any classroom or class would dictate more people that would be left-handed or not? Yeah, it's by chance, right? It's, you know, I know that a lot of you chose to take this class because you wanted me as a teacher, which I'm honored. Some of you didn't, you know, like, you were more, you wanted to make sure you had this other teacher, and then you were subjected to have me, which I hope you enjoyed having me. But just because certain things take place doesn't necessarily mean we're going to do it. So, you know, each class could yield a different number of left-handed students. It's going to change, but there's no characteristics of nature or the world of education that is going to be indicative of us having more left-handed students in a class, unless the prerequisite to take a class was you have to be a left-handed writer. Okay? So each class will yield different numbers of left-handed students. Okay? Whether there's all or none or some, it's anyone in that region. Okay? Hey friends, you just getting on? We're just going to walk through page 75 and 76, and then being that you're here, you get the points for it. Cool. A student wants to select 40 different classrooms, this is number 2, throughout Creek, and count the number of left-handed students in each one. This student chooses classrooms arbitrarily as he wanders the west building on campus. Explain why this is not a random selection. Okay, so this person wants to pick 40 classrooms in the west building. Okay, now a few things that stick out. And I said this the other day, maybe you picked it up, maybe not. I can't walk out in the hallway and then come back in and pick 3 random people in this classroom. My mind and your mind and our minds as people, we can't do something random. Okay? Why would I pick what would make my mind choose these three particular students of this classroom, or why would I be able to pick 40 different classrooms randomly on this campus? I can't. Okay, our brains aren't wired to do random. Okay, I know we think it is, but we don't. Okay, so human beings are not capable of making a random selection. We have to utilize some sort of technology or randomness type of generator to make it work. And it's how we're wired. It doesn't mean we're broken. It just means that our minds don't work for statistical randomness. Now, I'm sure that there might be some human being that has lived on this planet in the however many thousands of years this planet's been around, that their mind was wired in a way that allowed randomness to take place. Okay, but as people as a whole, we can't just select random by us using our mind to pick. Okay, we're gonna have certain things that if I were to walk in a room and pick people at random, or if I were to, let's say we have, a big game and there's a full crowd of people in there, I can't randomly pick people. Okay, there are certain characteristics of a person that my mind is going to very quickly determine I'm going to choose this person, and it's not because randomness is taking place. There's just something that is appealing about that person. Then number 3, we're on page 75, 76, just walking through it. So just make sure you have these filled out. So humans can't choose random. Okay, it doesn't happen. Then number 3, it says traditionally ACT scores are normally distributed. Okay, with a population of 8, with a mean of 18 and a population standard deviation of 6. Okay, so let's talk about this. Why on number 3 would we have a normal distribution? Okay. Why would the ACT create a normal distribution? Just thoughts. Do what? To be fair. To be fair. Well, it's not really to be fair. The normal distribution comes from the scores. But I like your thought. So the ACT normal distribution really takes place. How many years has the ACT been given? Now, I will tell you, when I was in high school, you had to choose to take the ACT on some Saturday when they would offer it. You had to sign up for it. Well, sometime between me being in high school and you being in high school, now the schools are offering the ACT as one of our testing days. Are there people that choose not to take it? Yeah. But do most people take it? Yeah. So we have lots of data. And this allowed us to create a normal distribution. And we have a mean of 18, and we have a standard deviation of 6 on this. That means that people would score between 68% of the population that takes the ACT would score between a 12 and a 24. Okay? That's just the nature of the test. Now, some of the testing data has improved somewhat. Okay? How many of you know somebody who had gone to some sort of ACT tutor or prep situation? I bet you every one of you knows somebody, if not you, has gone through some sort of ACT prep. okay? This takes place in more affluent areas than less affluent areas. If we went to a very, very poor school that families don't have the money to pay for extra help, that's going to be a little bit different. But, you know, Cherry Creek High School, we have a more affluent community than we don't. So we're on page 75, 76 when you get in there. So, so the mean, if I were to have letter A, if I were to say, what is the mean and standard deviation of a sample size 100, our mean is going to stay the same. Our mean is still going to stay as 18. But our standard, and we're going to call this is standard deviation, but we will start referring to it as standard error. Takes place a little bit differently, okay? So this would have gone with what our standard deviation had been, standard deviation that was given, over the square root of our population. That's a D. Okay, so the standard deviation that we had was 6, and we're going to go over the square root of 100. Well, the square root of 100 is 10, so we get 6 out of 10. So now we get our standard deviation changes to a standard error, which becomes 0.6. Now, what this means, my friends, does everyone feel comfortable to say that there's a lot of data on the ACT nationwide? Does this make sense? I mean, ACT has collected data. They release their information. You could go on their websites. You could find information about the ACT at any given time. It might fluctuate a little bit year to year, not a whole lot, but they keep it as all of the data that's gone in. Okay, so if you had billions upon billions of people who have taken the ACT since I was in high school, it's going to take an awful lot of people doing much better than 18 to move that average over a little bit. So it's going to stay, that 18 is pretty firm. But what's going to happen is as I start collecting data on people, my standard error gets closer and closer and closer and closer to the standard deviation. So how you kind of look at this is the green is set up as our group right now. But if I were to change this to orange, if I were to incorporate the standard error, think about what the standard error is. Plus 0.6 minus 0.6. So notice we are starting to converge in from both sides to approach what the actual mean was when I start selecting people of samples. Okay, we approach it. We're not incorporating the entire standard deviation. We're creating something now that's called a standard error. Standard error starts getting in the way of what the standard deviation had been, so it's going to be modified. That standard error changes based on the number of people we're talking about. I mean, if I picked, 100 million as my sample size, we're going to be really close to 18. I mean, that 0.6 might become 0.00006. So we're really close. I mean, we're hugging what our actual population mean is. Okay? So create all 7 new standard deviations. Okay, so basically it would be this, and then this is 0.12, this is 0.18, this is negative 0.12, negative 0.18, and I'm off on my graph because obviously 0.18 is really far away. So we're just jumping, our standard error is just going out just a little bit in accordance to what our standard deviation actually had been. Okay? Now, letter C says, what percent of all random sample size 100 will possess an average ACT score greater than 20? So, if I pick this 100 as my sample, okay, so that goes with our standard error. Okay, we want to now figure out, could we could we select a group of 100 randomly selected people that have a score greater than 20? So think about where this greater than 20 would fit on our thing. So this becomes 18.6. I guess that should be 1.2 and then 1.8. So if I'm coming out, our 20 is basically here. Okay, so now we're trying to figure out this scenario. Okay, but we want the standard error to be put in. So we're going to use the standard error versus the standard deviation. And our standard error in this case is the 0.6. So if we were to jump on our buddy Desmos, this is going to be a very unlikely scenario that would take place, because I want all 100 of my randomly selected people that I pick to score above a 20. Now, so let me show you this two different ways, just so you can kind of fathom what's really kind of taking place here. So our buddy Desmos comes in. And I'm going to do our normal distribution based on our mean and our population. Okay, so if I hit my plus button, this is my normal distribution based in this case. Okay, this is saying the entire population. So if I were to say, hey, what's the probability that that an individual would earn a 20 or greater, you're talking about a 36% chance. But because now I have randomly selected 100 people, I need to change my normal distribution to incorporate the standard error rather than the standard deviation. So I'm going to change my standard deviation from 6, I'm going to change that to 0.6. And then this becomes my normal distribution based on that. And now if I wanted somebody to score a 20 or higher, look where 20 lives here. If you look on our graph, we're seeing this normal distribution with this thing. Now I want the probability that our 100 people selected at random, that all of them would score of that 100 a 20 or higher. Look where the 20 is on my normal distribution. It's way over here to the right. So we're talking about move the decimal place 2 places to the right. So we're talking about a 0.04% chance that because I knew what my entire population mean was, which was 18, my standard deviation of the entire population was 6. But now, because we're going to randomly select 100 people, we're going to change our standard deviation to a standard error by using the original standard deviation divided by the square root of the number of people. And so this is a very unlikely event of taking place that I go and select 100 people, and with our normal distribution that we have, of those 100 people are going to score 100 or a 20 or better on the ACT. Okay? Does that make sense? All right, and that's where I kind of goofed up a little bit yesterday, and I apologize. But that's what's basically taking place. Does that, friends, do you feel comfortable with what I've just done? Okay? So if we're talking about a population and a population mean and a population standard deviation, that's just the normal distribution. But then if I say, okay, I know the entire population does this, what's the chance that I randomly go and pick a certain amount of people? Then I'm going to change that to the standard error, which is based on the original standard deviation divided by the square root of the number of people we're choosing. Okay? All right. Problem number 4. Problem number 4 says, assuming that a basketball player has scoring that is normally distributed with a population mean of 24 per game and a population standard deviation of 4. Okay, so our normal distribution based on this scoring of 24, and that's 28, and that's 32, and this is 20, and this is 16. Okay, so this is the entire population of scoring, and we have our normal distribution. What percentage of all of his games will result in that person scoring 29 or more points? Okay, so this is going to be a normal distribution where I'm still using the standard deviation that's given. And the reason I can do that is we're talking about one person. So if I know that my mean that was given was 24 and my standard deviation that was given as the entire population was this, even if I said, oh, well, I'm going to use that new equation stirrup had, so that's going to be the standard deviation divided by the square root of n. Well, look what takes place. I'm going to do my standard deviation divided by square root of 1. Square root of 1 is 1, so I get my standard deviation back. Okay, so it doesn't change at all. So then we want to know, what's the chance that this person is going to score 29 or more in this situation? Because we're talking about one person, it's going to work. So I'm going to go to my normal distribution, and I'm going to change my mean to 24, and I'm going to change my standard deviation to 4. And then we want to know what's the chance, and let's do this, what's the chance that our person scores 29 or more points? So the chance that our person scores 29 or more points, because we're talking about just the individual, is roughly a 10.6% chance that our person is going to score 29 or more points. Okay, the reason I did not change that to the standard error was I was only talking about one person or one selected situation. Okay, it's not multiple. Okay, now create a normal curve or sampling distribution for a season of 81 games. Okay, so this is going to change a little bit. So now, what we're basically doing is we still have our one person, and this last one was the probability they scored 29 or more points in a singleton game. But now we're going to say, hey, okay, what's the chance that our person in this case does it over 81 games? Okay, so this basically is one game. Now we're going to change it to 81. So I'm going to go 4 divided by the square root of 81. Square root of 81 is 9. And so 4/9 is now my standard error. And the nice thing is Desmos is going to allow us to use 4/9 as our standard error. So if I go back into Desmos, I'm going to change this 4. I'm going to go 4 divided by 9. Okay. And 29 more points. Oh, but then they want to change it to 30 or more points. So what's the chance that our individual player that we had having 24 points scored in a game, changing our standard error from our standard deviation to standard error, so now we're at 4/9. So we're talking about 7.8 times 10 to the negative 42nd power, which means I have 0.0 with 41 zeros, 7/8. So it's very unlikely that this particular player, who is normally scoring 24 points per game with a standard deviation of 4 as their overall numbers, excuse me. Now we're going to say, hey, they're scoring, we're looking at 81 games. 81 games is going to be a little bit different. Okay? At 81 games, now we have, 4/9 that we're using. And so that changes it a little bit. So it's very unlikely that our player that we had all this data on for the years of playing basketball goes from scoring 24 points with a standard deviation of 4 to scoring 30 or more points in all 81 games. Okay? And then, is there any questions so far? Do we feel comfortable with what we're doing? Makes sense? Okay. Number 5 says a psychological evaluation. We like psych in this class, I guess. Psychological evaluation is performed on memory retention. Memory retention scores are normally distributed with a mean of 200 and a standard deviation of 40. Okay? So if we create a normal distribution based on this, this is just going to look like this. $120. That's what our normal distribution is basically going to look like. So calculate the probability that an individual memory retention will score between 150 and 200. Okay, so let's make this normal distribution first. So we're going 200 and a standard deviation of 40. We do this, that's the normal curve based in this situation. Okay? So now we're going to say, all right, we have one individual. We want to know what's the chance they score between 150 and 250. Okay, so one standard deviation to the left takes us to 160. One standard deviation to the right takes us to 240. So we're going beyond that. So I can go down and I click my little square, and I'm going to change my minimum value to 150. And I'm going to change my other square to 250. So that's the area there. So we have... So 150 to 250, 240, 200. So it looks like we have a 78.9% chance that somebody scores within that region. Okay? So we have a 78% chance that they're going to score somewhere in there. And then if we were to change our sample to 25, so we're going to go 40 over square root of 25. What's the square root of 25? 5. So 40 over 5 is 8. So now I'm going to change this 40 to an 8. And that's now what this normal distribution looks like. And then calculate the probability somebody is going to score. So if I were to go walk into a room or go into society, somehow randomly select 25 people, if this is all true, basically the probability, because I'm choosing 25 people, because I'm now going to change my standard deviation to my standard error, means I have a 99.9999% chance that those 25 people I selected are going to score between 150 and 250. Okay, so it changes the parameters quite a bit. Okay? So friends, do you feel comfortable how the standard error is taking place? Standard error means I'm now going to start selecting people based on the population, and now what's the probability that certain things could take place? As the sample size rises, explain what happens. As my sample size gets bigger, so this is E, I guess 5E, the standard error is going to fall. And the reason why that's going to take place is I take my standard deviation divided by the square root of n. As n gets larger, the fraction becomes a smaller number. Okay? What happens to the mean in this situation? The mean stays the same. Okay? Now, this is what you have to think of. So this particular class, statistical analysis, has now been offered for 5 years here at Cherry Creek. every year it's been offered, we have 5 sections of it. Okay, so basically we've had 25 sections of this class since we started it. Okay? Each class, let's just say, had 4 or 20 people in it. Well, 20 times 50 is 1,000. Okay? So we could probably look at the data of these classes overall and look at, because first semester is already over, we could look at the average first semester score and find the mean of that. We could then find the standard deviation of the first semester scores. And then an individual of, like, say, this class, you're not going to move the mean too much. Okay, because there's an awful lot of people who have been a part of this class. But like an entire class, like if everyone in this, like let's say the average grade of this class that we have found is an 80% with a standard deviation of 7%, and I'm just making arbitrary values up. Let's say everyone in this class earned 100%. Okay, that's going to change our mean a little bit. But if I wanted to say what's probability based on our information that we know, what's the probability that everybody, so let's just kind of goof around with this. Let's just say that we knew stat analysis over the past 5 years has brought us this information, okay? And I do a normal distribution. Follow me? So then I could say, well, what's the probability, if I do this, this is just the whole population, what's the probability of somebody earning a 90% or higher in this class? So if I just talk about just a person in general, that would mean based on our information, which my information is not correct, I'm just making it arbitrary, which basically comes, a person has about a 7.7% chance of earning an A. Now, what's the probability of Stirrup's first period earning? So there's 29 people in here. So what's the probability of us doing that, of earning above an A, because there's 29 people in there. So if I were to say to you guys at the very beginning of the year, what's the probability based on this information that everyone earns an A? Can we all agree that 7.18 times 10 to the negative 15th power is 0.0, where I have 1407, is the chance that everyone earns an A? And I just made up something, but I basically took what our class is and dealt with it. So then the very last one, as the sample size rises, explain what happens. The probability average of our random sample between 150 and 250, it's going to rise dramatically based on that last scenario. Okay, so on our last scenario, when we had done the math that they had, if I wanted to create, let's just do this. Let's take away our root 29 and just make it our normal distribution. If I were to say, hey, what's the chance that somebody earned between a 78 and a 84? The chance that someone earns between a 78 and 84 in this class as an individual based on the population is a 32%. If I were to then change my 7, if I were to change my 7 to square root of 29, because there's 29 people enrolled in this class. So what's the probability of this class? I get to a 93.7%. I incorporate more people as a chance. So I have a larger area. So I have a 93% chance of this taking place, which is pretty great. The reason why it changed so dramatically is because 7 over root 29 is a much smaller number than just 7. Okay? So, I mean, if I were to kind of do a side-by-side comparison, I don't know how this is going to work. Normal distribution, 80, comma, 7. And I'm going to go 78 to 84. Okay, and I have to kind of play around with my graph a little bit to make it work. Oops, I don't want that. So basically, the chance of our original class that we had somebody earn the score within that, so looks pretty good. So because our random sample, because we change our standard error means that we're coming closer and closer to the mean, basically means that we have a much higher chance as a whole versus an individual, so it's going to rise. So friends, I hope that cleared